Hello and welcome! Yay! It's time for chemistry! Yay! Thanks for the follow, Austin. Hopefully you guys enjoyed your wonderful spring break. Just you, Caden. There's only it'll get going. It'll get going. It'll get going. It's not as off topic as honors chat. I think it's always just randomly just want to hear yourselves type, I think. Hey, Bryce. How was your break? Hey, Maggie. Maggie, how's your forced quarantine? Hey, mountain biking is a great activity. No. Something I've always wanted to get into, but never really had the stuff to do it, or like the people or things. I don't know. Don't want to buy a bike. Expensive. Bunch of themed days. I can only imagine, Maggie. I can only imagine your household. Yeah, that's for sure. That's what I mostly know, and I don't really have a friend group that mountain bikes, so I don't know if it would be worth it for the investment. Maybe if I could get like my brother into it. Oh, TJ. I feel bad for all the seniors who don't get to do prom. Yeah, I know Draper has a bunch of great trails, and I know Max is like way into mountain biking and stuff. Like it seems fun. Like I would enjoy it. I enjoy riding bikes and stuff. But I just don't have things. I wouldn't know where to start. Morning, Isaac. Surprised you didn't call us nerds. So, spring break was good. I took a nice break. I didn't do anything. Schoolwork. I should have. Sorry. I missed you, Isaac. Did you tune into the BYU streams? Did you catch one of them? I couldn't remember if you actually looked for one of them. That's all right, DJ. I appreciate your honesty. Okay. So that one was a while ago. I'm glad you got to sleep, Kara. Hopefully you caught up on some sleep. You could just leave the streams going. You didn't have to watch the streams. Oh, that's good. Get some driving practice, Isaac. Get the working towards that license. Assuming you were the one that was driving. Don't they? Are they not doing like an open beta for everyone? I haven't looked at the details for Valorant. I thought there like is a date where everyone gets access. Oh, okay. I thought they were doing it. I thought they had a date set to have everyone. My PC's fantastic. I haven't had any issues with it yet. I know, but isn't there a date where they're just doing open beta? Yeah, I got all the emotes. Don't want to lose your valence electrons. One-fifth way. There's gonna be in like, I think towards the end of this month, like so many people are gonna hit the 10K that I'll just have to spend the entire stream dabbing. It'd be sad if you lost all your valence electrons. Then you'd just be like every other metal. All right, we're up to 26 people. That's good. That means people are tuning in. Tuning in. So, so hopefully you guys have a chance to work a little bit in your review books. Lauren said she didn't do anything, but hopefully she maybe looked at her review book. So hopefully you guys have spent a little time in the review books. The AP, if you didn't catch my writing in my announcement in Discord, College Board did officially come out and say how they're going to structure the AP exam. Looking at it something. Opening it is the next step, Lauren. Just kidding. So the next, I'm trying to think. The AP exam is on May. They moved it back a little bit. So it's on May 14th, which is the second week in May. And they're doing 2 long questions, and you're getting 45 minutes. And technically, they said it's open book or open note, which is interesting. I don't know how they're going to structure that. I'm going to double check on that. But, Lewis structures. Yeah. We kind of reviewed that. That was a little bit with Unit 2. So we're going to dive into Unit 3 today, which is intermolecular forces, solid things. For sure, Max, you can use a calculator. It is fast. It's only 45 minutes. But even then, I still feel like... I don't know. It's gonna. It should be okay. I think you guys will be fine, but we'll see. Also, let's look at Canvas right now since I've got the Canvas pulled up. It's going to be 2 long questions, Joel. I think is what they've decided. 2 of the. So usually the typical AP exam, right, in the past is 3 long questions and 4 short. But you had like 105 minutes to do that. So they're just breaking it down to just 2 long questions and giving you 45 minutes. So each question takes about 20 minutes to answer, which is what it has been in the past. I think 21 minutes, if I remember the math. So it's going to be 2 long free response questions covering units 1 through 7, not 8 or 9. So, all right, so let's talk about the calendar. Not the calendar, but let's talk about AP website, right? So remember on the modules, this Thursday night, you need to have, let's see, intro's good, quarantine to-do list done, AP review streams, we'll put Unit 3 Part 1 here after today. We already did the 2015 exam. So the 2016 exam, right, remember that's due on Thursday. So if you haven't started the 2016 exam, make sure you get that done by Thursday night. I'm gonna add the grading key here probably this afternoon or tomorrow. But I do want you to dive in and do the 2016 free response. If you already done, great, work in your review books. If you haven't done it yet, make sure you start it. I think I did make a note. You can skip number 3, E and F. But otherwise, you should be able to do most of it. And then, reminder, this is due Thursday, and we'll go over the answers and questions and things like that on Friday. So we got that coming up. That'll be the plan for this week. We're going to do Unit 3. Unit 3 is the longest unit of the AP course. So we're going to go over Unit 3 both today and Wednesday. Grades are not updated, Isaac. So I'm going to be working on that. I should have time to do that tomorrow and Thursday. That's kind of why I'm not streaming every day, is so that I actually have time to update grades. So I'll be working on that tomorrow and Thursday, so I can hopefully get that totally done. BYU ends tomorrow. Their last class is tomorrow, and so I'll have a lot more time to get stuff, to work on stuff. That'll be one less thing for me to have to worry about. My last BYU class is tomorrow. So then I'll be able to focus more on getting your stuff. I'll have more time to get your stuff up to date. So, thanks, Isaac. Appreciate it. You guys can do it too. AP exam. We're down. It's a month from tomorrow. So we have 1 month. Tonight we're just reviewing. We did OChem last week. So we spent 2 full lectures doing OChem. All right, so that's it for kind of calendar things. Let's go into Roman numeral 3, Unit 3 review. So, like I mentioned, Unit 3 is all about intermolecular forces, kind of, and then it really goes into some of the details about that. So, let's dive in. Let's jump in. Unit 3 review. Let's brush out some cobwebs. So, letter A. Intermolecular forces. So, number 1. Let's just call it types. Maybe we'll call it structure and strength. All right. So our first intermolecular force that we're going to go through is London dispersion forces. Okay, now London dispersion forces are a little tricky. We often underplay London dispersion forces, but they're actually super, super important. For most molecules, London dispersion forces are actually the strongest force. So the few key things we want to know about London dispersion forces. They are present in all molecules. Right? Present in all molecules. They're most significant in nonmetal atoms and nonpolar molecules. Okay, so the most significant in the nonmetal atoms and nonpolar molecules. We're going to do a lot of little Roman numerals today. We got a lot of details. They're stronger with more total electrons. Right, stronger with more total electrons. So some examples of that. Something like C2H6 is going to be greater than CH4, right? So larger molecule, both of these molecules are nonpolar molecules, just carbons and hydrogens. Carbons and hydrogens are always nonpolar. And so this molecule, because it's larger and bigger, is going to be stronger than, say, this molecule. Why are they more significant in non-polar? Isn't it they just don't have permanent dipoles? I should say it's the most significant force. So when we're talking about nonmetals and nonpolar molecules, they don't have any other forces between them. The only thing that's holding together nonmetal atoms and nonpolar molecules in the liquid or solid state are dispersion forces. There are no other forces that are keeping those molecules attached, right? So if we have liquid C2H6, the only thing that's attracting one C2H6 molecule to another C2H6 molecule is a dispersion force. There aren't any other forces. So that's why I mean they're the most significant in these nonvalent nonpolar molecules. But they are present in all molecules. So all molecules have dispersion forces. So to kind of describe what a dispersion force is real fast, right? So a dispersion force is the idea that your polar molecule or your nonpolar molecule, basically the idea that you have this electron cloud, right? So your molecule is surrounded by electrons, and that when two molecules bump into each other, though that electron field gets dispersed temporarily, it's polarized, and so as it's polarized, you get temporary attractions. When we say we have this more total electrons, the way that people usually say that is we say that it is more polarizable. It's kind of the catchphrase there. You're good, Naya. This is all we've got so far for the notes. Sarah, hopefully I answered your question with that. Okay. Good. Yep. All right. So that's all I wanted to say about. Let's talk about dipoles. So little letter B. Oh, children. So you guys still see that if you're trying to cut that down. Little letter B. So when we talk about dipoles, let's do dipole first. So this is when the I should say, in polar molecules, there is a dipole. Now, what's a dipole? A dipole is you have a partially positive end and a partially negative end. So with dipole-dipole forces, right, in polar molecules, there's a dipole. A dipole is a partially positive end and a partially negative end. Example of a polar molecule is just something like HCl, really simple. Right? The chlorine atom is more electronegative, and so the chlorine pulls on the electrons in this bond, right? This bond is made up of two electrons that are being shared. So the chlorine pulls on it, and that makes the chlorine end a partially negative, and the hydrogen end a partially positive. Right? So the chlorine end is negative, the hydrogen end is positive, and so if you have one HCl like this and another HCl like that, this attraction between them is our dipole-dipole. Right? Okay. So dipole-dipole. Let's see. They are stronger when the molecules are more polar. So Lauren, that's a good question. In a given molecule, the partially negative and the partially positive, those have the same magnitude, right? But if we looked at a second No, they're the same. They balance out, right? I think is what your question was. Yeah, but if we had a different molecule, we could have a different molecule that could be more or less polar than HCl, right? HBr, since bromine is less electronegative, HBr is less polar than HCl is. Right? Remember, polarity is a result of the difference in electronegativities of the atoms in a bond. Wouldn't you get like a partial charge if what Lauren was saying was true? Yeah, you would. The whole molecule would end up having an overall partial charge rather than being neutral. All right. Let's talk about C. So this is one that we don't actually talk about that much through the year, but the AP test kind of talks about it. So I wanted to bring up dipole, ion dipoles. We'll call them ion dipole. So ion dipole, right? Ion dipole forces is the idea that a polar molecule can attract to an ion. Right? Yeah, sorry, little c still, little c. It's not a very good little c. Little b, little c, ion dipole. So little I. A polar molecule can attract to an ion. So for example, this would be like if we had HCl and we had like a sodium ion, right? There's actually an attraction between this sodium ion and the chlorine end of the HCl. Right? So this is called an ion dipole force. This explains a lot of like why things dissolve and why compounds dissolve in other compounds. We talked about how ionic compounds are soluble in polar molecules. So we've shown water. That's the one that we usually draw, is we draw the water molecules with the oxygen end facing towards the positive ion and the hydrogen end facing towards the negative ion. But it can happen with any polar molecule in any ion. And it's called an ion dipole force. They're technically a little stronger than dipole-dipole, but that's not important. You usually don't get very many questions about this. I just don't want you to get thrown off if you see the term ion dipole. And then the last one, along the same lines, I guess it's not the last one, second to last one. Along the same lines, we can have a little letter D, where we can have dipole induced dipole. Right. So dipole induced dipole is when a polar molecule causes a non-polar molecule to form temporary partial positives and negatives. Let me try to explain this. So if we have an HCl and we bump it into, say, like a CH4, right? So if this HCl kind of bumps in, right, what happens is, because the HCl is polar and because there's more negative over here, when this negative end bumps into this end, the electrons in the HCl get shifted over to the side. And so what we get is we get a very temporary sloshing of the electrons. so that we get an attraction okay, so we get kind of we have our normal one here, so we get this induced temporary dipole. Because the chlorine unit is negative, it causes a very temporary positive and negative in this nonpolar molecule to form. Yeah, so we have a dipole induced dipole. Oh, I guess, yeah, temporary positive and negative. Yeah, we could say a polar molecule causes a nonpolar molecule to form a temporary dipole. So, Max, that's a great question. It depends on a lot of factors. It's stronger than dispersion forces if you're looking at molecules of similar sizes. But it's weaker than dipole-dipole. So it's kind of like in between dipole-dipole and dispersion. But it's weird because you're mixing multiple substances together. And when we talk about intermolecular forces, we usually focus on just a pure substance. But this happens in mixtures. You can get this attraction. So. Okay. And then letter E, our good friend, hydrogen bonds. Right? So hydrogen bonds, as we remember, we have to have, so you must have H bonded to N, O, or F. It's more or less, it's like an extreme case of dipole-dipole. Right, it's the idea that you have HF, HF, and then you get this attraction. Question: how long until they're able to normally? No. It's like a matter of picoseconds, Isaac, if I'm not mistaken. Very temporary. So what I mean by that, Lauren, is that it's an exaggerated case, right? So hydrogen bonds are stronger. So they're strong. They're the strongest intermolecular force. So if you're comparing multiple molecules and you're trying to find which one has the greatest intermolecular forces, if one of them can form hydrogen bonds, it's most likely going to be that substance, right? So hydrogen bonding, and the reason why I call it an extreme case is basically because this molecule is polar, but there's something about the HF, HN, HO bond that is just really polar. There's more to it than that. It's just this weird special case of HN, HO, and HF that this attraction is just abnormally strong. And so that's why I mean kind of like an extreme attraction of the positive-negative end. Hopefully that makes sense. Okay. Cool. So dipole-induced dipole, hydrogen bonds. That's it. So those are our 5 intermolecular forces. 5. I mean, 3 of them are just kind of weird dipole-dipole cases. So we have London dispersion forces, sometimes just called dispersion forces. Right, those are caused by temporary polarizability of your molecules, induced dipoles, etc. They're stronger when you have bigger molecules. Then we have our 3 cases of dipole forces. We have dipole-induced dipole, dipole-dipole, and ion dipole. Right, all 3 of those interact with when you have a polar molecule. And then lastly, we have hydrogen bonds, which is this really specific case of hydrogen directly bonded to nitrogen, oxygen, or fluorine. And So van der Waals forces, if I remember correctly, van der Waals forces are kind of a weird. So van der Waals forces, the AP test just doesn't want you to talk about. I'm trying to remember. They're really similar to. Dispersion forces? Yeah, I don't know. So van der Waals forces aren't on the AP test. You shouldn't see or use the term van der Waals forces. They're just really weak attractions between things. They're more like a static force, if I'm not mistaken. But I would have to look more into that. I know that it's a different thing. So don't use the term van der Waals. Done. Yeah, only use dispersion or London dispersion. Yeah, don't use the term van der Waals. Yeah, they do use it in biology all the time, which is kind of weird. I don't know why. I that's something I need to look more into. So yeah, I think it's bigger when you talk about it's more important when you talk about really large molecules like you deal with in biology, but I'm not sure. Okay. Make sure I've got everything I need. Because geckos. They got their sticky feet. They stick to the walls. Alright. Letter. Wait, number. This was a lot. Okay. Number 2 on intermolecular forces. Number 2. Let's call it particulate representations. So little a. So the strength of excuse me, strength of intermolecular forces determines properties. Okay, namely things like melting and boiling point, as well as vapor pressure, yep, so those two. So with melting and boiling points, stronger equals greater, and with vapor pressure, stronger forces equals less, right? So there's a direct relationship between the strength of your intermolecular forces and the melting and boiling points. If you have stronger intermolecular forces, stronger attractions, you're going to have a higher melting and boiling point. If you have stronger interactions and stronger attractions, you're going to have a lower vapor pressure. Right? Remember vapor pressure, pressure of the vapor, how much it tends to evaporate. So, ionic crystals are strong. They have high melting and boiling points. Low vapor pressures. They're brittle. They conduct electricity. Only as liquids. Or aqueous. There isn't anything after small Roman numerals. That's as far as I can go on my outline, Isaac. Yep. And again, just as kind of a recap about our ionic crystals, right? Remember, we have positive, negative, negative, positive, positive, negative, positive, negative, positive, right? The reason why they're brittle is that if, this gets shifted over, then we have positive attracted to negative, or positive next to negative, and it explodes. Yeah, I guess I could do that, but I've never had to go that far, Isaac, so I always design my outlines to never have to go that deep. All right, questions about ionic crystals, ionic structure properties? All right, letter C. Little letter C. Covalent network solids. Oh, so vapor pressure, remember, Haley, vapor pressure is the pressure of the vapor. Sorry, it's stupid. The vapor pressure is when you have a liquid, right? A liquid evaporating. And so the more that a liquid evaporates, the greater pressure it's going to exert on the container. And so if you have something that evaporates really easily, it's going to have a high vapor pressure. And if you have something that doesn't evaporate at all, it's going to have a very low vapor pressure. Yeah, but Philip, nobody knows or Zach, nobody knows the Greek alphabet. All right. Yeah, just small font. I could do that too. I love how you guys are stuck on the outline. All right, covalent network solids are the strongest. Okay, so we know in covalent network solids, right? This is when you have there are. We're not talking about intermolecular forces, right? So. Right, they're held together by all covalent bonds. There are some intermolecular forces. That's probably a little bit of an exaggeration, but all covalent bonds. So, like, we've talked about diamond, graphite, silicon, silicon carbide, silicon dioxide. Colligative properties. Oh, Isaac, colligative properties technically aren't on the AP test. But we will briefly mention them tomorrow. I mean on Wednesday. Yeah, we'll get to them Wednesday. Okay. Let's see. Okay. Cool. So basically, they're hard, rigid, brittle, etc. The AP test does. They mention that graphite is soft. So I'm going to do my best to just do a quick sketch. Of like a diamond versus graphite. And these technically should be triangles, but that's okay. So what they want you to recognize is that diamond has this very brittle three-dimensional shape, whereas graphite, it has layers, and the layers can kind of peel off of each other. And so that's why graphite is soft, like in your pencil leads and things like that, is because the layers can spread. But if you try to melt graphite has an incredibly high melting point because you have to break those covalent bonds in order to get it to melt. So graphite is soft because the sheets break off, but it still has a very high melting point. So they do want you to understand the difference between like a diamond crystal structure and graphite crystal structure. Okay. So let's contrast covalent network solids with molecular solids. Something like ice. Okay, so in molecular solids, we have molecules held to each other by intermolecular forces. Okay. So in something like ice, right? Okay, so so they are weak because intermolecular forces are weak. Right? So when you melt water, when you boil water, you're not breaking apart the O and the H. You're breaking apart one water molecule from another. You're breaking the hydrogen bond. Okay, so your water stays together, stays bound by covalent bonds. Those covalent bonds stay together. And when you have steam and water vapor, right, you have individual water molecules all floating around. But one water is attracted to another water by a hydrogen bond. Okay, and that hydrogen bond is what breaks. And relatively speaking, a hydrogen bond is like 1,000 times weaker than a covalent bond. Covalent bond is way stronger. Same thing, ionic bonds, metallic bonds, those are way stronger than your intermolecular forces. For the most part. There's always exceptions. Do I want to say anything else about that? So they have low melting points. They don't conduct electricity. Yeah. Okay. So that's molecular solids. Letter E, little letter E. Lots of details. Unit 3 kind of gets rambly because it talks about a lot of stuff. Okay, so letter E. All right, little letter E. Metals, metallic solids. Metallic solids are strong, right? For the most part, there are some weak ones. Biggest things you want to point out about metallic solids is they're good conductors. Good conductors of heat and electricity. Because they have the sea of electrons. Right, they have these mobile valence electrons. No, I haven't watched Tiger King. We just finished Good Place. Kennan's not in a good spot, Caden. I mean, he's okay. He's still a lane bully. But the meta doesn't really work with him right now. Yeah, we just finished it. It was great. I really liked it. All right. So metallic solids are strong. They're good conductors of heat, electricity. Yeah, we loved it. My wife and I really liked it. Hopefully. He's still annoying. All right. So metallic solids are good conductors of heat, electricity due to the presence of free valence electrons. Alloys still conduct. Just kind of like a random tangent that they put in the guideline here. But are less right. So we talk about metals. Metals are also malleable and ductile. So remember, alloys are a mixture of metals that still has metal properties. So things like brass and bronze and steel, those are mixtures of like copper and zinc, copper and tin, iron and carbon, right? So we took notes on those. That was in Unit 2. We have some notes on alloys. So if you want to go back and look at that. It's in Unit 2. We drew some pictures of those. So Lauren, I would go back to those notes, the Unit 2 notes, if you want to go double check those. Roman numeral 2. Okay. And the last thing we got to talk about here, letter F. Larger molecules can form intermolecular forces with themselves, right? Which is kind of weird. Oh, Joel, back earlier in the year. So if we imagine that we have like a really large molecule, like really, really large, like imagine you have, a bunch of carbons connecting, but you want to represent that as like this really long string of carbons. So really long string of carbons, atoms, hydrogens, oxygens, etc. If this molecule gets really, really long, it can actually fold in on itself. And as it folds in on itself, it can form intermolecular attractions with itself, right? So if you have this really long carbon chain and you have like a COH here and you have like a COH there, it can actually bend on itself and it can form attractions. Yeah, this is most significant when you're talking about proteins, DNA, cellulose, all these really long molecules. So these are usually called like macromolecules. This becomes super important in like biology and biological applications. But yeah, so mostly we're just going to say that, you know, these larger molecules can form intermolecular forces with themselves. So they're called non-covalent interactions is kind of the fancy term they use. Okay. Let's see. We got to fly through this next one in just a couple minutes. So this is stickers. I love my children. No. We got to do big letter B. Octagons. You can have, but those aren't large enough, Micah. I mean, I'm talking like really big molecules, like proteins, that are hundreds, if not thousands, of atoms large. All right, big letter B. States of matter. All right, kind of take a step back and talk about solids, liquids, and gases. I know this should seem pretty obvious and straightforward, but I still want to make sure that we get all these details so that we know it. And it's a big part of Unit 3. All right. So solids can be crystalline, where they have a regular repeating structure. Or they can be amorphous, which is a fancy way to say irregular. So solids can be crystalline, regular repeating structures, or they can be amorphous. So in both cases, right, the solid particles are mostly immobile. Right, they're stuck in place. Right, they'll vibrate and maybe move around a little bit, but in the solid crystal structure, you're not going to have atoms moving past one another. Right. They're going to be locked in some sort of a crystal pattern. Okay, and even if that pattern's irregular, you're still going to have just molecules and atoms locked in place. They're going to be vibrating and moving, but they're not going to be moving past one another. Letter B. Okay, liquid particles are close together, but tumble past each other. Right, and so this, like, the stronger the forces are, you'll get things like viscosity and those other properties, but we're not going to really dive into that. I like tumble. Tumble's a great word. I guess I'll put a little note here. Solids and liquids tend to have similar densities. Let us see. Yeah, it's a great visual word. Okay, so gases. So gas particles are in constant random motion. Right? It's about 1,000 times less dense than solid or liquid. That's true. Hey, that works. Right? How test lessons volume. We need it. This leads into we need to talk about pressure, temperature. Where are we going with this? What's coming next? PV equals nRT, but we're saving that to Wednesday. Everyone, PV equals nRT, PV equals nRT. Max, we're not talking about plasma. All right, so this is as far as we want to get today. This is where I wanted to get, so we're good. But on Wednesday, we'll dive into PV equals nRT. We'll also talk about separating mixtures. We'll talk about some spectroscopy stuff, give you guys a good review of that, and maybe teach you a little bit. And that's kind of the big ideas. So that's everything. Ooh, I got followed by a spicy boy. Okay. Work on the practice exam. If there's any questions on either the practice exam or the review book, or basically just anything you're working through, I'll be available this afternoon. So feel free to hop into the Discord, ask questions, and then I'll upload that grading key. Make sure to get the 2016 exam done by Thursday. We'll do more of review on Wednesday, but that's pretty much it. Hope you guys enjoy getting back into the mode of school. Hopefully your other teachers aren't giving you too much of a hard time. So let's do it. Have a great day. Bye guys.